Hi, I'm Sebastian Mader from Penn State University, and this is ESC 216, Advanced Scanning Probe Microscopy. So this will be Lecture 1 in our Characterization and Testing of Nanotechnology Structures and Materials section. Our outline for today's topics will be an overview of scanning probe techniques, scanning tunneling microscopy, then we'll go into AFM or atomic force microscopy, and finally an example of instrument operation. Characterization on the nanoscale. Using nanoscale materials and understanding them are two quite different things. Modern tools help us to manipulate and characterize the materials at the nanoscale. There are two notable innovations. An FESEM, which is a field emission scanning electron microscope, allows us to somewhat see at the nanoscale by detecting different electrons given off from a sample and probe interaction. And then scanning probe microscopes, or SPMs, which kind of allow us to feel at the nanoscale. They involve a probe interacting and kind of feeling a force between the probe and the sample below. If we look at a timeline, a brief history of nanocharacterization, on the far left in 1933 we see the advent of the scanning electron microscope. Fast forward to around 1980 and we see the first scanning tunneling microscope. Continue on a little bit more into the later 80s, we see the advent of AFM, some other more sophisticated detection techniques such as optical beam bounce, and as we continue on we see different modes of atomic force microscopy. So really, scanning probe microscopes as a set of tools are fairly new. They started in the basically the mid-80s. So as we said, there are a variety of different scanning probe microscopes. We can think of that as a family, scanning probe microscopy. And some of those instruments, some examples would be a scanning tunneling microscope, an atomic force microscope, dynamic force microscope, and scanning near-field optical microscope. And there are actually a little bit over 24 different types of scanning probe microscopes. But all of them have one thing in common, that is that there will always be a probe moving relative to the sample surface, and then we will measure the interaction between the two. We could be measuring different things. It could be current, capacitance, forces, even absorption or heat flow, but there will always be that probe moving relative to the sample and some measurement of the interactive force. Some measurement of the interaction between the two. Here are three examples. Scanning tunneling microscopy, we'll measure tunneling current. Atomic force microscopy involves mechanical measurements such as attractive and repulsive forces. And magnetic force microscopy measures differences in magnetic fields and strengths between the tip and sample. So let's begin our discussion with scanning tunneling microscopy in a bit more detail. An STM utilizes a conducting tip, usually tungsten or gold, and it's sharpened ideally to the point of a single atom. There's a bias voltage applied between the tip and sample, and the two are brought into very close proximity, a bit less than a nanometer, so we're talking single-digit angstroms. At this distance, the electrons can actually quantum mechanically tunnel through that gap between the tip and sample. The tunneling current that occurs between the tip and sample is actually what we use to measure surface topography. Now, to understand tunneling a little bit better, again, it is a quantum mechanical effect. Let's look at a few diagrams. The diagram on the top left, we see two metals separated by some type of gap, some type of barrier. Normally, the electrons can't overcome that barrier on their own. If we narrow that gap down in the bottom, we see that if we get extremely close, there is some quantum overlap of the, if you think about probability densities, and electrons can and do tunnel back and forth between the metals through that gap space. Another way to have tunneling instead of the extremely close proximity of the tip and sample is if we apply a high voltage, and in this way, by applying that voltage, we're able to bias the electrons enough so that they can overcome their work function and actually tunnel from one material to another, and that's known as field emission, while the bottom example was our example of tunneling. A little bit more about tunneling here. If we look on metal 1, we're looking at basically the probability of finding an electron in the material. And again, if the gap is small enough, the electron has a small but substantial probability of crossing over from the first to the second metal. Why do we need to be so close? Again, in the absence of that electric field, that field effect, the materials need to be extremely close together, less than 1 nanometer, in order for electrons to have a significant probability of tunneling between the two materials. So how can tunneling current be used? How can we use this phenomenon in a scanning tunneling microscope? Well, here we see these gray atoms represent the bottom of our scanning tunneling tip, and then in blue we have our sample below, and the red dots represent the tunneling current between the two. What we see on this graph is, let's say we're resting here at maybe 0.8 nanometers or at 8 angstrom distance. If you move up or down, okay, so if that distance increases slightly or decreases slightly, you see huge changes in the tunneling current. So what does that mean? It means because tunneling current only occurs at these very small distances, and because it's extremely sensitive to changes in distances, we can use that to gather very sensitive, high-resolution information about our samples below. As far as a principle of operation, we can adjust the gap distance between the tip and the sample by using a piezoelectric material. We'll talk about that later. And then we maintain the tunneling current at a desired set point by adjusting that gap. So in other words, as this gold tip is scanning across our sample, instead of the tip moving down to maintain that let's say 0.8 nanometer distance, we actually move the sample up a proportional distance as to this step height right here, and that maintains the set point. And the trick to doing that is using a piezoelectric capable of making those fine incremental adjustments. So the tunneling current, as we said earlier, changes dramatically, exponentially, with the distance between the tip and the sample. The changes are detected by a feedback loop, which keeps the current constant by adjusting that tip surface separation. We just mentioned that. And then the signal, the tunneling current detected, provides us with a high resolution information about surface topography and or electronic states on the surface material. Again, in all these tools, the probe rasters across the sample. So if we can imagine this tip rastering across the sample and keeping the same relative tunneling current, and therefore the same relative distance, then the sample is going to have to move. It's going to have to be moved up and down in order to maintain that set point. And if we record this data and we scan a sample, one line, the next line, the next line, we can end up plotting that to form a 3D representation of our conductive surface below. What can be measured? Well, we see this equation, we see the tunneling current is equal to the charge on the electron, then the bias applied between the tip and sample. Again, that can help overcome the work function and allow tunneling to occur more readily. Then we also have a complex function describing the electronic structure of the sample. Basically, by playing with these and measuring or knowing these, having knowns on the right side of the equation, and then measuring the tunneling current, we can result in determining the topographic or height features of our sample. We see if no bias is applied, then the relative energy levels are as such. If we put a bias on the tip, let's say a negative bias, we can actually help electrons to tunnel from the tip to the sample. You can see this downward slant showing you that the basically energy levels have been lowered. If you put a positive bias on the tip, then actually electrons will tend to tunnel into the tip from the sample. And these two things we can have occur back and forth and measure those changes. Another example, as far as current imaging, tunneling spectroscopy, this is when we have filled and unfilled electronic states, and they can be examined by varying the tip sample bias. So, as we showed prior, a negative bias allows electrons to flow into the unfilled states of the sample. A positive bias on the tip allows electrons to flow out of filled states of the sample and, of course, into the tip. At each XY data point, we acquire data at multiple positive and negative biases, and this allows visualization of the local electronic structure of the sample. So this is a form of scanning probe microscopy, but it's actually a spectroscopic technique, and it's giving us information of localized electronic states. Now some requirements and limitations for a scanning tunneling microscope. One thing worth mentioning is every tool has its pros and cons. It has, places where it shines and is the best tool around, and other places where you would want to select another tool. It's the same as you would select a hammer to drive in a nail, and you would select a screwdriver to turn in a screw. But if you switch the two, you're not going to have the desired result. So in an STM, the sample and tip must both be conductive. Okay, that's quite limiting. It requires isolation from vibration, along with many other characterization tools. It requires precise positioning mechanisms, such as the piezoelectric below. It requires the ability to measure very small currents. Well, we have that in an STM. And samples must be very flat. Can't say atomically flat, but definitely on a nanometer scale they need to be extremely flat. Sample surfaces should also be well defined and stable over time. So if you want to increase stability, you can do things such as remove the air, so do your STM operation in a low pressure environment, and also you can cool it using cool your sample using liquid nitrogen or some other means to basically reduce vibration and increase stability. Good tips are difficult to prepare. Only about 20% of tips actually produce meaningful results in STM. There are two general ways to prepare the tips. You can do kind of a cut and pull technique with a metal wire that actually gets quite sharp tips. And another way is an electrochemical etch shown here. as far as the tips, here is actually a scanning electron microscope image of one of these tips that was fabricated with that cut and pull technique. The sample in the tip, as we said, must be conductors or semiconductors, and that question might be, how sharp is an actual tip? Well, again, it depends on the technique employed, but hopefully these are in the low tens of nanometers or less. STM can be done in air, but the best results are at ultra-high vacuum. Another reason for this, and we talked about stability, is samples must be stable so that oxide layers do not form, and also ultra-high vacuum presents absorption of contaminants from ambient air. So on the left we have an ideal tip, on the right we have the real tip, and what actually might be occurring in a lab at a normal working environment, standard temperature and pressure. So a real tip is not going to end with one atom as a single point, and your surface is probably going to be contaminated, definitely with some water, just because of the water content in the air. There's always going to be a little level of hydration there. So here's an example of some interesting surfaces for STM analysis. There was a surface reconstruction of silicon in the 111 plane. This was a kind of an early victory for scanning tunneling microscopy. The image clearly showed the arrangement of the atoms on the reconstructed surface. This was the first time this was ever done, and these measurements were done after annealing and also using ultra-high vacuum. Another example was imaging highly oriented pyrolytic graphite. These images were used to explain the packing of the layers relative to each other, and then there are some questions, for further investigation you could try. How do the layers of graphene lay on top of each other? Do the atoms line up or not? So this is something you could check out if you have further interest. Just to point out, graphite is basically stacked sheets of graphene, which are both of which are materials composed only of carbon atoms. So now let's delve off into another type of scanning probe microscopy, and this is called atomic force microscopy, or AFM. And we'll go into a little bit more detail about some of the hardware components, tip sample interaction, modes of operation, and some of the pitfalls and image artifacts which may arise while imaging a sample. So first of all, how did we get to an AFM from the advent of the STM? Well, the problem was there were a lot of materials we were interested in characterizing, but they were not conductive. So the goal was to come up with a technique similar to STM, but have it somehow be able to characterize non-conductive samples. So the question was, are there other tip sample interactions we could use, and how could we measure those changes? How could we measure that interaction? And below is one of the first papers from the physical review letters kind of introducing an early atomic force microscope. So here is one of the early AFMs, and it's pretty clever. What they did is they started with something they knew, scanning tunneling microscopy. So here's the tip. Below it, instead of having your sample, they developed a gold foil lever. So now, as long as you keep these two close enough, of course, you can measure tunneling current. Below this, you have a diamond tip and your non-conductive or insulating sample. So it's kind of 1 degree of separation here. You're still using STM, but now you have a cantilever that can trace a non-conductive sample. So this is pretty clever. Again, there is use of a piezoelectric to move your sample below the diamond tip to allow you to kind of raster and scan all areas of your sample. And there'll also be a feedback control loop, and we'll talk about both of these in more detail in a few slides here. Traditional microscopes are limited by lens quality and diffraction loss, okay? And this is true for, you know, a magnifying glass. This is true for optical microscopes. It's true for SEMs and field emission scanning electron microscopes as well. Scanning probe instruments, however, don't use lenses at all to focus light. Instead, we use a small probe, we raster it across a sample, and we capture the information from that tip-sample interaction as some type of signal. If we keep track of where we were scanning, X and Y coordinates, and then we plot the information we gathered as a Z coordinate, we end up with a three-dimensional kind of map of our sample surface. Again, the AFM is one of many scanning probe tools. All of them use a nanoscale probe, scan over the surface. The AFM can characterize surfaces on a scale of about 0.1 nanometer to 100 microns. So the largest possible object that you could scan in one session would be about 100 by 100 micron scan. The smallest feature you could resolve would be about 0.1 nanometers or an angstrom. And that's actually to be more clear, that 0.1 nanometer resolution actually only occurs best in the Z or height, the Z channel information. As the name implies, the instrument measures the forces acting between the tip and the sample. It's commonly used as a type of microscope due to its ability to gather high-resolution topographic information. And the combination of being able to measure forces and providing us with a nice spatial image, high-resolution spatial image, makes AFM a very versatile characterization technique. So now let's dive into some of the actual hardware and components used in a modern AFM. So here's the basic principle of operation. These are the primary components we need. This happens to be an optical beam bounce type of technique for sensing, for detecting the data. So if you look here, this is a front view of our cantilever with a sharpened tip below. A cantilever you can think of as a tiny diving board, and it's coming out at us right now, and the tip is below interacting with the sample. The piezoelectric scanner is going to move the sample left and right in the x-axis, forward and backwards in the y, and actually up and down in the z to try to maintain a constant force or constant cantilever deflection as it is rastered underneath the probe tip. Now, if that cantilever, that micron scale diving board, is deflecting or moving up and down or kind of rolling right or left, we're going to sense all those changes with our position sensitive detector. And the way we do that is by using a laser. So typically you have to manually adjust the first mirror, then the second. You center the laser spot on the position sensitive detector, and you'll start with a set point. We'll talk about this more later, but you would start with a set point, and then when you reach a feature, you know, maybe it's going down or maybe it's going up, you'll have a certain level of deflection. That data, that difference in your set point and where you ended up, will be stored as your Z channel data. And basically there'll be a feedback loop with your computer that will send a signal to the piezo and tell it how to compensate. You can think of it as a compensation network. So in the most basic mode, AFM measures the surface by monitoring the deflection of the cantilever in the Z direction. Detection is done by measuring the signal produced by a segmented photodetector. And typically you would have 2 segments, and sometimes you'll see 4. So you can measure basically up and down deflections, but also kind of right and left pitching deflections. far as hardware, obviously we need that sharpened tip on the end of a cantilever. We need a way of monitoring that deflection. The example we saw was laser beam and detector. We need a piezoelectric and a scanning system, and then we need a computer-controlled feedback loop to kind of coordinate the movements of the piezoelectric, moving the sample below that sharpened tip. There are different types of AFM tips. There are different micromachining techniques used to produce some inexpensive and reasonably sharp tips. Below we see 3 common tip configurations. We see standard on the left, which is kind of a pyramidal. Sharpen is another example. And then an ultra lever on the far right, which might be a wet etch technique. But all tips have a finite radius, and this end radius is generally what determines the ultimate resolution of our AFM. So not only do you want a very small tip radius, but you also need to consider the geometry of the tip. It makes a difference if the angle of the tip is 20 degrees or 40 degrees or 90 degrees. A standard tip is about 3 microns tall, pyramidal, with 20 to 30 nanometer radius. And both these images were taken with a scanning electron microscope. The top one is a side view of the cantilever with the tip, and then this one is at a higher magnification. This is about 64,000 times magnification, and taking a little radial measurement there. The diameter shown here is 66.47 nanometers. So if you extrapolate that, the arc length, it might be about 20 nanometer radius. Here again is a larger picture of that cantilever at the side view. There's another technique for building an AFM tip, and that's called an EBD, or electron beam deposited tip. This is an improvement to the others we described. Basically, an E-beam deposits a carbonaceous material, and step by step by step, eventually we end up with a very sharpened and smaller radius. So here we just zoomed in, we see that carbonaceous build up to a finer tip. The ultra lever will be manufactured using microlithography techniques. It offers high aspect ratio and a 10 nanometer end radius. And then as far as detecting cantilever deflection, there are a variety of ways we could do it. We already saw the optical lever or beam bounce technique, but you could also use STM as long as you had a conductive metal on top of here, as we saw in the kind of the early first AFM. Optical beam bounce. You could also measure changes in capacitance or even changes in piezo resistance. Here's an image again, just showing the optical cantilever kind of at work. Basically, we have our detector, our laser. It hits the cantilever, is reflected up to the position-sensitive detector, and this is used to detect changes and maintain the tip-sample interaction via the feedback loop. Down below, of course, we have our piezoelectric tube scanner. The optical lever magnifies motions of the tip. That's another thing to point out here. The cantilever to detector distance is actually thousands of times larger than the cantilever deflection. So what that means is the magnification factor can approach about 2,000, and the optical lever can theoretically obtain very low noise levels. So this is similar to if you had a laser pointer on your desk and you were sitting in the back of the room and the wall was 50 feet ahead of you, you could swivel or turn your laser pointer just a few inches, and the beam spot on the wall would appear to travel, maybe 20, 30 feet. So that's what we mean by this cantilever deflection and how it magnifies the motion by using that laser. This technique is inexpensive and it's fairly accurate compared to other modes of measuring samples on the nanoscale. As far as the detector itself, it's going to be a photodiode. It will convert incident light into current or voltage, and the incident light that we're interested in here is that of the laser beam, which is reflected off the cantilever. The detector will typically contain 2 to 4 photodiodes, as we mentioned previously. And it's actually the comparison of signals from the 2 or 4 photodiodes which create a position-sensitive signal and allows us to measure deflection of the cantilever. So when you're first setting up the tool, the way you can tell if your laser spot is centered is if the signal of A minus B equals 0. Here's just another example with an upward deflection and downward deflection, and showing you the signals coming from the detectors. These are the actual, this is the actual information that is saved and eventually plotted to give you the kind of 3D spatial image of your sample topography. The piezoelectric scanner is obviously made up of piezoelectric materials. A piezoelectric is a material that changes shape in the presence of an electric field. In other words, if we apply a voltage to this piezoelectric, it will actually expand. If we reduce that voltage a bit, it'll contract a bit, as far back as to its initial kind of 0 voltage state. The high electric fields actually produce only very small changes in the size of the material. These are sub-micron changes. So since these can be precisely controlled, we can precisely position the sample and move it quickly but in a stepwise fashion below the cantilever and probe. The tool operates using tube scanners. These allow for movement in all 3 directions. We need the X and the Y for rastering, of course, and we need Z movement in order to maintain that constant contact or constant cantilever deflection. Metal electrodes on the tube of the material allow for voltages to be applied. As far as positioning the sample, we use an active platform to control that position. This is an improvement compared to other characterization tools such as profilometers, where you have a stationary platform. The active platform is the tube scanner. It's made of piezoelectric material. Again, it will expand or contract according to the applied voltage. 4 outer electrodes control the X and Y motion, while an inner electrode controls the height or Z information. And then there is a feedback loop or compensation network required to monitor the deflection and keep that deflection constant by adjusting the height of the sample or cantilever. The system could be analyzed in 3 different areas as far as positioning the sample. The tube scanner will control the height of the sample. The cantilever and optical lever will measure the height of the sample, and the feedback loop, again, will keep the cantilever deflection constant by adjusting the applied voltage to the scanner. So here's an image showing our feedback loop and kind of how this works in conjunction with the cantilever, the sample, the piezoelectric. So as the piezoelectric is moving the sample, let's say from left to right, okay, in the x direction during one line scan. The cantilever is going to start to deflect upwards. As soon as it deflects upwards just a bit, the laser spot will move up on the photodetector. Now that detector voltage, that voltage will be above the original voltage, which was the set point. The difference between those two, okay, the original set point and the new detection voltage, is called an error signal. This error signal is what is stored at that XY coordinate, and that signal is also sent to your compensation network or feedback loop. And this is then incorporated, and a signal, a voltage signal, is sent down to the piezoelectric, basically to tell it to, if we're rising up here, the piezoelectric would contract and go down in the z direction in order to try to maintain that constant cantilever deflection. So that is the purpose, and that's how the feedback loop or compensation network actually works. Okay, here's just another example of the feedback loop. We can see movements over time. If the detector voltage is equal to set point, there's no error signal, it's perfectly flat. There's no action required by the system, and the piezoelectric doesn't move. If they're not equal, then there's going to be an error signal, and via the feedback loop, there must be a response to bring the error signal back to zero. And by applying that piezoelectric with the appropriate voltage, that response will be made. So there are three components to a typical control system, and this feedback loop is no different. There's proportional, which reacts to the current value of the error signal. There's integral, which will react to the sum of recent errors. And then derivative, and this is reactions to instantaneous rate of change of the error signal. So each of these components will basically be trying to compensate and respond in real time and send that information via the feedback loop to the piezoelectric. So as an example, proportional depends on instantaneous value of the error signal. So if it's high, it's going to be sending information to bring it back down. Integral will take a look at recent history and try to figure out which direction it needs to return back to. And then derivative will depend on the rate of change of the error signal and help adjust it accordingly. So each type of control addresses a unique aspect of the system, and tuning is usually required to achieve robust control. In other words, as an operator of the tool, you can manually adjust, type in new numbers, proportional, integral, and derivative components of the feedback loop. And that's probably one of the main differences between a novice user and someone who's been operating with an AFM for several years in research, etc. As far as tuning the feedback loop, we typically start with P or proportion equal to 1 and integral and derivative equal to 0. A good technique is to increase P until overshoot just begins to occur. Overshoot means that your cantilever is riding over the top of, let's say, a hill, a certain height feature, and then it's not coming down fast enough. It's not maintaining contact with the backside of let's say, that little hill or feature on your sample. If you see that occurring, then you need to start to decrease the P just below the maximum stable value, so just before there's overshoot. And then you can increase I and determine the effect. But a good rule of thumb is I should be about 0.3 times P, and generally we don't even need to adjust D. So again, these are all parts of the feedback loop which you have control over as an operator of the tool. Okay, next up will be a more detailed discussion about possible tip-sample interactions. So if we think about some of the forces which may be occurring or present between a tip and sample. We might think of things like covalent bonds, ionic or electrostatic bonding, hydrogen bonding for sure, if there's going to be some water content in the air. Van der Waals forces, definitely, as the tip and samples approach each other, basically their electron clouds are going to have some type of overlap and interaction. And there could also be hydrophobic interactions between the tip and sample. The tip and sample may experience many forces. Each force will act over its characteristic length scale, and some will be attractive and some will be repulsive. Again, some of them may be long-range or short-range electrostatics. There could be short-range polarization. Dispersion forces may play a role within a few nanometers. There'll be van der Waals forces at very close distances. Pauli repulsion, or basically electron repulsion. And also capillary forces. This is one that many users kind of neglect to consider, that there is a thin film of water on top of all samples and tips, which are playing a role in determining the interaction force here. As we said earlier in this lecture, not only is AFM a type of microscope, but it can also be used to measure forces between a tip and a sample surface. The reason this data is useful to us is because we can relate it to the surface energy of the sample. And there are many useful ways to incorporate that information. So there are many theoretical approaches to modeling this type of interaction, each of them kind of treating that interaction in a different way. And the results depend really heavily upon the geometry of the tip and the types of forces that you're actually considering and including in your calculations. One technique is the Lennard-Jones Potential. This is a simple model combining dispersion, attractive van der Waals forces, and then your Pauli repulsion forces. It's repulsion at very short distances from overlapping electron clouds. So if we look at the graph on the bottom right, it's basically a plot of the potential energy between the tip and sample as you approach. Well, going from left to right, it would be as the tip and sample are getting further and further apart. But if you imagine us approaching, and you can imagine, let's pretend the bottom of the tip is one atom, and let's pretend there's just one atom sticking out on your sample. As you approach each other, they'll first be attracted to each other. And the reason for this attraction is both atoms have a positive nucleus and both atoms have a negative electron cloud. So the electron cloud of one atom will be attracted to the positive nucleus of the other atom. And that continues as we get closer and closer, but then eventually we get into kind of a null region where the forces balance out. And if we continue to force the cantilever closer to the sample, then we'll have repulsive forces getting larger and larger. Here's another view of that graph with a bit more detail. This is showing kind of our general Lennard-Jones potential equation, where we factor in the Pauli exclusion, we subtract the van der Waals attraction. But you can see our overall potential, which we're calculating as a potential and forces between two neutral atoms approaching each other. The positive slope is telling us we have an attractive force, then no slope is, no net attractive or repulsive force. As we continue to push it closer, we get those repulsive forces. This Lennard-Jones potential model basically considers what happens when these two neutral atoms are approaching one another. It's a pretty good model, but of course actual tips and samples are not composed of single atoms. They have atoms arranged in some unknown geometry oftentimes. And we are simplifying the problem here. Another thing to point out is that when the interactions become when all the interactions between all the atoms are considered, potential is going to vary even more, and the force will vary. So actually distance becomes a more critical factor here. Again, this is kind of how we come up with that Lennard-Jones potential model. We imagine the tip mounted at the end of a cantilever. Since a cantilever is a bit like a small diving board, it's flexible, we can say that it behaves as a spring with a certain spring constant. And as that tip approaches the surface, it'll feel some type of force due to that tip sample interaction. But of course, that spring constant, that spring force, we can also imagine that is working on the tip. So you can come up with a way to balance these forces and therefore model all the forces acting on the tip as it approaches the sample. This is the general concept for how the Lennard-Jones potential was developed. This is just giving different examples of, here's a neutral state, attractive net force, and repulsive net force, and the deflection that we would see in the cantilever. Here also we see kind of the importance of understanding the material properties of your cantilever, and as well as the spring constant and things of that nature. Or if we approach a sample with a strongly rigid cantilever, we will actually have nano indentation. Whereas a soft cantilever, we'll actually see the tip snap down to the surface and level out as we continue to lower it, and finally we'll get a deflection. So this would be a cantilever with a lower spring constant, basically being lowered down onto a material that's harder than itself. Basically, for this to occur, and this is often what you want so that you don't damage your tip and or sample, you have to make sure that the spring constant of your tip is less than, it works out to a force which is less than the forces between the atoms in your sample. Otherwise, you'll move those atoms around and you might damage the sample, and you'll most likely contaminate and or damage the tip as well. A little bit more on the cantilever and spring constant. Here we're approaching our sample, we're decreasing that height, and we see this is with a very, very rigid cantilever or high spring constant. The cantilever is so rigid that the tip doesn't snap to the surface. Okay? Now, if we turn back and think about the signals and the measurements, then consider the signals or variables measured by an AFM instrument. We have cantilever deflection, and we also said piezo movement could be considered a signal. So again, we generate a voltage whenever that laser beam is off-center or different from the set point. And what we want to see is, what do these signals look like exactly as the tip approaches the sample surface. Now, if you were investigating force distance curves, we would see that the data collected as that tip does approach the surface, contacts, and retracts from the surface, this data could be used to create our force distance curves. So those curves we saw earlier, which were modeled using the Lennard-Jones potential, would actually be, an accurate depiction of what's occurring. And we can get those, and we call those force distance curves, and we can get those by collecting the data during this tip approach, contact, and retraction. The collected data will be a series of Z data points, and with that delta or error signal. These curves will give us information about the forces between the tip and the surface, and the data points could also be converted, again, by plugging in the numbers into these equations, we would generate our final force distance curve. So again, this is basically what we're describing here, is how to use the AFM not as a microscope in this case, but as a way of measuring force distance curves and therefore determining information about the surface energies or interaction forces at your sample surface. We go back, we take a quick look at our principal operation just to remind everyone. We have our laser, our mirrors, our cantilever, our position sensitive detector, our computer and controller, incorporating that detected information, the error signal, sending, using the feedback loop to determine what appropriate voltage to send to our piezoelectric, and then that piezoelectric will be moved the corresponding distance in the z direction. And all the while, of course, the piezoelectric is moving in the x and y direction, following a normal scan pattern. And the distances and the number of data points collected can be controlled by you, the operator. So if you want to scan a 30 by 30 micron scan, 30 by 30 micron box, you would just type that in. Then you could select the number of data points you want to basically gather from that small area. Of course, if you want to zoom in, what you're actually doing is taking the same number of data points but in a smaller area. And that'll give you a higher resolution and higher magnification image. So I think this is a good point to stop for Lecture 1, and we'll pick up here with the beginning of Lecture 2 for Advanced Scanning Probe Microscopy in your course ESC 216.